All right, so continue with 9.2. We're looking at that vertical motion model, which what that does is it kind of models if you were to throw something up in the air or kick something and what we'll do is think about what happens as time goes on. You'll have some starting height, and we're not modeling actually the motion of the object. We're modeling the height of the object as time goes on. The object could go straight up and down. It could go out like a punt of a football. That doesn't really matter right now. We're looking at what's going with the height of the object as the seconds go on once you kick something or throw something. So think about that. Time will be our independent. Height is our dependent variable. And you have some sort of starting height. Maybe you start, you punt the ball a couple feet off the ground. And think what happens again. Whether it goes straight up or down, as time goes on, the height of the object is going to go up. It's going to get to its max point or its vertex, and then it's going to start to fall and come down until we hit the ground. And that's what we're looking for when we talk about hitting the ground, when your height would be 0. So this would be your time. And think about that. As time goes on, right, the ball is going to go up. Again, it could be going straight up and down. It's not the flight of the object here that we're worried about. So as time goes on, the object's going to get up to its max height, and then it's going to start to fall and come down. And what that will do is that's a quadratic motion, which creates a parabola each end every time. And what that vertical motion model is it's similar to our y equals ax squared plus bx plus c, but we use some different variables here. H equals negative 16 t squared plus vt plus c. And what these variables represent, h would be our ending height. Okay, so we could be, you could be asked the problem, how long will it take to get to 10 feet? We'd plug it in here. How long it will take to get to hit the ground? That means it'd be 0, or our maximum height. T in this case is our time. And by the way, our height is in feet. Our time is in seconds. So we're not in meters per second. We're in feet per second, which that's why we have that negative 16. That's our force of gravity, negative 16 feet per second per second. All right, if we were doing using the metric, we'd have negative 9.8, but here we're negative 16. Our velocity, it's our initial velocity. When you throw something up, it has an initial velocity when it leaves your hand. When you kick something, if you drop something, your initial velocity will be 0. Okay, but if there's an initial velocity that's in our feet per second, that goes right here in front of our time and our B. And C, sometimes it's known as S. That's just our initial height, the starting height of the object once we get going. So an example of that is if you take from page 555 in the textbook, there's an example. I'm modifying it slightly, but what it states is that we're going to shoot some t-shirts with a slingshot into the crowd, and it's going to have an initial upward velocity of 72 feet per second. Once that slingshot lets it go, it's released from the slingshot 5 feet above the ground. And then what I did was, okay, let's find the time it takes to reach its max height. All right, this is kind of just a sketch over here we'll talk about in a second. So we want to know the time it takes to reach the max height. Max height is our vertex, right? The time would be the x value of the vertex. What is the maximum height? That would be our h value of the vertex. And then how long will it take for the t-shirt, if nobody caught it, to come all the way back down and hit the ground? So always think, as soon as you see max height or min height, we're looking at the vertex. So I plug into my quadratic equation. Okay, let me erase what's on this side, and we'll go back and plug that in. Give me 1 second here. What I do with my eraser. All right, so if I start out with that information into my quadratic, to my vertical motion model, so h is going to equal negative 16 t squared plus our initial velocity was 72, so plus 72t plus from our initial height of 5. Okay, so there's what I'm working with. And if I want to find the time it takes to get to the max height, again, think about that. If I'm going to start at 5, it's going to go up, it's going to get to a max height, and come back down. So I want to know this time right here. Well, that's my x of symmetry. So the time it takes to get to the max height will be x equals the opposite of b over 2a. That'll be the x value, or the t. And I just plug that in there. So I go ahead and plug in. So it becomes negative 72, right? The opposite of b over 2a over negative 32. I grab my calculator. I do the math. It ends up being 2.25 seconds. So that would be the answer to the first part. But to find the time it takes to get to the max height, I ended up with 2.25 seconds. Now, if I want to know what is the max height, think about that. If I plug in 2.25, that's going to give me that max height. So I go to my calculator, and I just plug in 2.25. So what is the max height? Again, a lot of this stuff is just calculator work. I type in negative 16, so my height will equal negative 16 times 2.25 squared plus 72 times 2.25 plus 5. Hit enter. H ends up being, and I did it already, whoops, I just erased it, but I think it's 86 feet. So my max height was right here. So sketching that out, all right, if you're looking at this, I'm at, right, at 0 is at 5. At 2.25, I'm all the way up here at about 86. Okay, I just sketched these out as best I can. There's my axis of symmetry coming through. And then I found the two pieces that was asked here. What is the max height? It was 86 feet. And then they might ask you some other questions. How long will it take to hit the ground? Well, right now, we don't know how to solve that algebraically. So all we can do is use a table of values, which my hand just kind of erased a bunch of it. But use a table of values, plug in some ordered pairs, and see what happens. When do we hit 0? So when I plug these in, when I plugged in 4 for my time, I got 37. So 4h was 37. So at 4, I was at 37 feet in the air. When I plugged in 5, I got to negative 35 feet. So I'd be below 0. So I knew that my time then would be somewhere between 4 and 5 seconds. And right now, that's a good enough answer. You know, somewhere a little bit bigger than 4. If I can, again, guess and check and get closer to it if I need to. But somewhere between 4 and 5 seconds. How long will it take to hit the ground? A little after 4 seconds. In a few sections, we're going to actually learn how to find that exactly. Okay, so a quick recap on that. In your vertical motion model, we know our h is going to equal negative 16t squared plus vt plus s. All right, negative 16 is the force of gravity, time in seconds, initial velocity, initial height, ending height. Okay, we have a parabola. It's going to go up, back down. Okay, and to find the time it takes to get to the max height is the opposite of b over 2a. And then to find the actual max height, which is going to be the vertex, I just plug that value in for t. That will give me the max height. How long will it take to hit the ground? Sketch it out. See when you're approximately hitting your x-axis, which would mean your height is 0. All right, check those out. There's a couple on the 9-2 packet for you to do. Again, right now we can't exactly find that time. We're just estimating as best we can. All right, I'm going to get back to you guys in a little bit with another video for today. Just giving you probably an example or two of how to solve a few of the problems, and that should be it. All right, keep working.